Let's talk about ordered binary trees. We're going to talk about how to create them, the rules to follow in searching and creating them, searching through a binary tree, why to use them, and what is wrong with simple ordered binary trees. If you have never worked with trees before, I would recommend checking out my tree basics video. And if you're wondering about tree traversals, I also have a video about tree traversals. I will continue to put all the other videos about trees down below because I also plan on doing many other videos about trees. So once those come out, they will also be linked in the description box. What is an ordered binary tree? An ordered binary tree, I mean, we all know that trees are hierarchical structures instead of linear structures. And an ordered binary tree kind of adds some of that hierarchical structure to the tree. So when you look at the root, you can see that anything to the left subtree is strictly less than the root, and anything to the right subtree is equal to or greater than the root. And that holds for any root that you look at on this tree. So if you look at the root of this subtree right here, we can see this, the subtree rooted to the left, anything in this subtree is less than this root, anything that is right to this subtree is greater than the root. But then anything in this greater subtree is less than this root, and anything in this right subtree is greater than this root. So it's a really interesting way to set up a tree. And the reason that you do this is so that when you search through the tree, you're not looking at any unnecessary items in a tree. So if you had this tree in a non-ordered binary tree, the worst case times complexity of looking through an unordered tree is n. So you could look at every single item in a tree if it's unordered to find the item that you're looking for, or maybe it's not even in the tree and then you have to look at every single item to realize that it's not in the tree. However, when you're using an ordered binary tree, the worst case time complexity of the tree is the height of the tree. So if I'm looking for 34, I would come up to 35. I would say, okay, 34 is less than 35, so I'm going to go to the left subtree because it's less than 35, the root. And then I have this new root, and I see that 34 is greater than 30, so I'm going to go over to the right subtree. 34 is greater than 33, so I would go to this right subtree, and I would see that there's nothing there, so I would be finished searching after visiting 3 nodes. However, if this was an unordered binary tree, I would have to look at every single item in this tree through whatever traversal that I was doing, which that would have been a pre-ordered traversal. I would have had to look at every single item in this tree to see that 34 is not in here. So that would have been a search of n. However, I only had to look at 3. The worst case is that I had to look at the height of the tree, and that would be the height. Now that we've talked about the reason that you use an ordered binary tree, let's get into the issue with non-balanced ordered binary trees. So let's say that we are starting a tree, so we add in 2. And then, so let's say we added 2. And then the next item that we're going to add in is 10. So that would go to the right because it's greater than 2. And then we'll add in 12. So that goes to the right because it's greater than 10. And then we'll add in 34. And that goes to the right because it's greater than 12. And then we add in 43, and that goes to the right because it's greater than 34. Now, if we're searching through this ordered binary tree, which it is an ordered binary tree, if we're searching through this, the height of the tree equals the number of items in the tree because this happens to be skewed over to the right. So when I'm searching, big O of the height of the tree is the same as big O of the number of items in the tree. So the worst case time complexity of a non-balanced ordered binary tree is the number of items in the tree. There's no way to guarantee that this is a balanced binary tree. So while on the average case, this offers you a better time complexity than a linear search or a non-ordered binary tree, it doesn't guarantee that. So how we get around this issue of the height of the tree possibly being the number of items in the tree is with balanced trees. So self-balancing trees, like an AVL tree, is a way to solve this issue. So my next video will be about AVL trees, but before we get into AVL trees, we have to completely understand ordered binary trees. So let's go back up to this slide, just so that now we understand why we use ordered binary trees and the potential issue with ordered binary trees and how we're going to move on from ordered binary trees into AVL trees. I just wanted you to understand all of those things. But now let's get back into this. So we basically went over how you search through an ordered binary tree, but let's just go through it one more time. So remember, everything to the left subtree is less than the root, and anything to the right subtree is greater than or equal to the root. Let's say that we're looking for 7. I would come to 35 and realize it's less than, so I'd go to the left. I'd come to 30, I'd say it's less than 30, so I'd go to the left. I'd come to 25, say it's less than 25, I'd go to the left. I'd come to 10, I'd see that it's less than 10, I'd go to the left, and I'd come to 7, and I'd say, yep, that's 7. So this is the node that I'm looking for. Let's look for something that we see is not in the tree. Say I'm looking for 13. So I'd come to 35, I'd say it's less than 35, so I'm going to go to the left. 30, it's less than, I'm going to go to the left. 25, it's less than, I'm going to go to the left. 10, it's greater than that, so I'm going to go to the right. 12, it's greater than that, I would try and go to the right, and I'd realize that I can't, so 13 is not in the tree. Let's do another example just to make sure this is totally clear. Let's do 43. So if I start at 35, 43 is greater than 35, so I'd go to the right. 43 is less than 63, so I'd go to the left. 43 is less than 54, so I'd try going to the left, and I can't, so I'd see that it's not in the tree. So that's how an ordered binary tree works. Let's construct an ordered binary tree. Let's say that we want to construct an ordered binary tree with 30, 35, 23, 10, 12, 44, and 50 in that order. So we would look here and we'd say, okay, I'm going to insert 30 into the tree. There is no items in the tree, so 30 would become the root of the tree. And then I would insert 35. So I would look at the root and say, is 35 greater than or less than 30? Say it's greater than 30, so it would go over to the right subtree and become the right child of the root. And then I'd insert 23. I would say, is 23 greater than, less than, or equal to the root, which is 30? It's less than, so it becomes the right, it becomes the left subtree. And then 10, I'd look at the root, say, is 10 less than or greater than 30? It's less than, so I'd move over to the left subtree. I'd look at this new root of this subtree, is 10 less than or greater than 23? It's less than, so I move over here. Let's do another one. At the end, we'll add 10 so we can see what happens when we add something that's equal to as well. Okay, now 12. We'd say, is 12 less than or greater than 30? It's less than. Is it less than or greater than 23? It's less than. We'd say 10. Is it less than or greater than 10? It's greater than, so it moves over to the right subtree of 10. Now 44. Is it less than or greater than the root? It's greater than, so we go to the right. Is it less than or greater than this new root 35? It's greater than, so we go to the right. There's nothing there, so we place it in the right subtree. 50. Is it greater than or less than 30? It's greater than, so we go to the right. Is it greater than or less than 35? It's greater than, so we go to the right. Is it greater than or less than 44? It's greater than, so we go to the right again, and we insert 50. Now 10, is that less than or greater than 30? Less than, so we go to the left. Less than or greater than 23? Less than, so we go to the left. Is it less than or greater than 10? It's equal to. So remember, if it's greater than or equal to the root, we go to the right. So we're going to move over to the right. Is it less than or greater than 12? It's less than, so we move over to the left, and we insert it here in the left subtree. So this is inserting into an ordered binary tree. We can see that it's not actually very balanced, but you'd still have to look at much less than the number of the items in the tree if you were searching for an item. So those are our ordered binary trees. Next, we're going to look at AVL trees in my next video, so if you're interested in that, you can look through the channel to see if it's posted. AVL trees take the time complexity of an ordered binary tree from O(n) to O log n, which is super awesome. So if you are interested in how to work with AVL trees, check out my channel. Please like and subscribe this video. Please like this video and subscribe to the channel if you found this interesting or you got some information out of it. I look forward to seeing you in my next video. Thank you so much for being here. Bye.